Having been introduced to the idea of finding area under a curve by using rectangular approximations, let's talk about some other options. If you think back to the problems that have been discussed before, all of those rectangles we used either to inscribe inside the curve or circumscribe about the curve all had the same width to those rectangles. But what if we could vary the widths of the rectangles, as we saw in other diagrams? That would enable us to get even a better approximation to the area under the curve. A Riemann sum uses this idea of the summation of the area of either inscribed or circumscribed rectangles, but allows the width of those rectangles to vary. The width of the largest subinterval, the width of the largest rectangle, is what we call the norm of the partition. And you can see there the symbol that we use to represent that. So if you think about that, as the width of the widest rectangle gets skinnier and skinnier and skinnier, basically the norm is approaching 0, and that allows the number of subintervals n to get larger and larger and larger and approach infinity. Basically, as the rectangles get skinnier, you are able to fit more of them under the curve. And hopefully that makes sense. So here's one option as to maybe what you could do with those rectangles to get a better approximation of the area under the curve. You'll see there's some fat rectangles here. Maybe we could break those up. If maybe we took this one right here and broke that one into skinnier ones, maybe we could fill some of the empty space up there. So the reason these are called Riemann sums, they're named for the German mathematician Georg Riemann. His work in physics and math became the basis for Einstein's work in relativity. The actual mathematical formula for how you create a Riemann sum, it is the summation as I goes from 1 to n. So I represents how many rectangles you end up having. The height of each rectangle is really going to be given by the y-coordinate to correspond to the curve. So if you think about it, remember all your rectangles are hitting the curve someplace. So the height of those rectangles can be given by the y value of the curve. So that's why the height of the rectangle is given by f of c sub I. So that accounts for the height of the rectangles. Of course, to get area of a rectangle, we need height times width. Delta x is going to account for the width of all of those. So let's take a look at an example problem. So here we have the curve 10 minus x squared, and we are asked to find a Riemann sum on the interval from 0 to 3 for the described partition delta and the given values of c. So take a look at what you're given. All right, you have x sub 0 being 0, right there. X sub 5 is 3, so there are your left and right endpoints of the interval. Now notice how you're told x1, x2, x3, and x4. That's telling you where each of the rectangles is ending. So that's going to allow you to figure out the width of each rectangle, because rectangle 1 is going to go from x0 to x1, so that's a width of 1. The second rectangle is going x1 to x2, so if you take a look at those values that you're given over here, that second rectangle is going to have a width of a half. The third rectangle is the skinny one. That's going from x2 to x3. That has a width only of 0.25. And then you could do the last two rectangles as well. Now notice how we're going to get the height of each rectangle. Notice how each of these rectangles is hitting the curve someplace. Right, these points at which the rectangle is hitting the curve are corresponding to those c values. So the c values are the x coordinates we are going to use to generate each of the heights of the rectangle. All right, so this first rectangle right here. We know the width is going to be 1. the height of the rectangle, we need to substitute the C1 value into the curve, into the 10 minus x squared equation, and that's going to enable us to find the height. The second rectangle, we already established that has a width of 0.5. The height of that one, we're going to have to substitute C2, which we are told is 1.25, into the function, and that's going to give us the height of that rectangle. And then we'll do the same for each of the others. So there's a few different ways we can actually do this. We can use our calculator to do all the work really for us by making use of the function notation that's built into the calculator. So let's take a look at how to do that. So as we do this Riemann sum, one thing you want to remember is we are generating an equation that is going to approximate the area under the curve. So see this approximately equal to symbol? That part's pretty important because what we're going to get as an answer is not going to be an exact answer for the real area under the curve. It's only going to be an approximation. So what we're going to do is go one rectangle at a time to figure out the width times the height for each of them. All right, so the first rectangle, and we'll keep flipping back and forth between the diagram and our work. So the first rectangle, remember, went from x0 to x1, so that had a width of 1. All right, so width of 1. Now we need to multiply that. Remember we said we were going to get the height of that rectangle by substituting C1, which was equal to a half, into the function. So this is the part we can let the calculator do. We don't necessarily have to number crunch each of these heights individually. So let's just write that up as we know we need to multiply that width of 1 times the function value at a half. All right, so that's your first rectangle. Let's go ahead and do the others. Then we'll turn to the calculator to do the work for us. Second rectangle goes from x1 to x2. So that has a width of a half. And the height of that rectangle we're going to get by substituting C2, which is equal to 1.25, into the function. So we have a width of a half times the function value evaluated at 1.25. That's giving us the height of that second rectangle. All right, third rectangle. So the third rectangle is the skinny one, this one right here. That's going from x2 to x3. So that has a width of just 0.25. And notice the height of that, it's actually this right endpoint right there. We're going to get that. Notice how C3 and X3 are really the same numerical value. So the height of that skinny rectangle we're going to get by substituting the C3 value, 1.75, into the function. So notice how it's not even consistent in terms of the placement of where the rectangle is hitting the curve, unlike what we saw with the left endpoint, right endpoint, and midpoint approximations. All right, so this is the skinny rectangle. It had a width of 0.25, and the height we're getting by substituting 1.75 into the function. 2 more rectangles to go. So the fourth rectangle, that goes from x3 to x4. So let's see, that has a width of a half because x3 is 1.75, x4 is 2.25, so that's a width of a half. And then the height of that we're getting from the C4 value, which is going to be 2. So we'll substitute 2 into the function. So we have a width of a half, and the height is going to be given by f of 2. So one more. So that last rectangle then, that's going from x4 to x5. So that has a width of 0.75. And the height is going to be given by what we get when we substitute C5 into the function. So C5 is 2.75. So this is what we can let the calculator do all the work for us. So let's go ahead and turn to the calculator and review how we can let that do the work for us. So what you want to do is under y equals have the equation. So remember the equation was 10 minus x squared. Then we're going to go back to our quit screen. And we're basically just going to type all that out. So we have 1 times, so now remember we needed to substitute 0.5 into the function. Remember your calculator will do function notation for you. If you hit the vars button, go across the top to y vars, into function, and pull up y1, and we're going to evaluate y1 at 0.5. So it looks like that. So it's essentially mimicking the f of x notation. So let's keep going for all the other rectangles. So the second rectangle had a width of 0.5. The height we were getting by evaluating the function at 1.25. Third rectangle, that was the skinny one, remember, that had a width of 0.25. And the height we evaluated by substituting 1.75 into the function. The fourth rectangle had a width of 0.5. Height we obtained by substituting 2 into the function. And finally, the last rectangle had a width of 0.75. And the height of that we obtain by substituting 2.75 into the function. And double check, make sure you get what I did. So we have an approximate area of 20.53125. Now later on you'll be able to find an exact value for that area under the curve. And once you learn to do that, you'll find that the exact area for this particular curve in between 0 and 3 actually comes out as 21. So you can see we're about half a unit off or so. So if you needed to include units, since we are talking area, this would be square units. So if you needed to include them, that's what you would use. Just a reminder, however, at the very least, you do need to have this approximately equal to up there, indicating that the area is really only approximately given by all that work that you just showed. So let's take a look at a more real-life example. Mrs. DeConte's trip to NCSSM each day takes 40 minutes. On one such trip, she noted her velocity every 5 minutes. So if you take a look at the table, we have increments going every 5 minutes from 0 minutes to 40 minutes. I've gone ahead and expressed those in terms of an hour because if we're going to use velocity as miles per hour, of course we need the units to be consistent. So you can take note there of the time of those minutes expressed in hours. So what we're asked to do is determine how far it is to get to school for Mrs. DeConti. So we're going to actually use both a left endpoint and a right endpoint approximation to do this. This is a type of Riemann sum, but you're going to notice it's not quite exactly a Riemann sum because since all of these time intervals are consistent, they're all 5 minutes apart, of course our rectangle widths are not going to vary. So this is not perhaps a true Riemann sum where the widths are allowed to vary. So what I've gone ahead and done is graph these on my calculator. You can see the time in minutes on the x-axis, the velocity on the y-axis, and we're going to go ahead and draw for ourselves a left endpoint, also in this case known as a lower endpoint approximation of the area under the curve. Now, if it's a left endpoint approximation, what you need to remember about how you draw this is that it's the upper left corner of each rectangle that needs to be hitting the points. Remember, we talked about that when you were first introduced to left, right, and midpoint approximations. So you do need to take care of how to draw these. So the first rectangle is going to go from like 0 minutes to 5 minutes. Right, that's really not going to have any height because if we need it to be a left endpoint approximation and it needs to hit that first point, well, it really has a height of 0. So that's like your first rectangle. So your second rectangle then is going to go from 5 minutes to 10 minutes. I just talked about it in terms of minutes because it would be a little bit easier when I graphed it. When we go to actually do the math, that's where we're going to use the decimal values, the expression in hours of those minutes. I just thought for the purposes of the graph it would be easier to do it in minutes. So the next rectangle is going to look like this. And this idea of you having to draw them out is actually a really important idea. And you're going to see this repeated in the next lesson, actually. So the next rectangle is going to go from 10 minutes to 15 minutes. So it's going to have to go all the way up here. Now this one happens to hit 2 points. That won't always happen. The next one's going to go from 15 minutes to 20 minutes. Remember, it's always the upper left corner of the rectangle in this case that it has to hit because it's a left endpoint approximation, a left-hand endpoint. Now going from 20 to 25 minutes, this is where we get another rectangle that really doesn't have a height because it has to hit that point at 20 minutes. So now we have a second rectangle that doesn't really have a height. So the next one's going to go from 25 to 30 minutes. Next one will go from 30 to 35. $35 to 40, then is the last one. All right, and notice how it's that last point in the graph, this one right here that doesn't really have a rectangle assigned to it. That's because it's a left endpoint approximation. Anytime you do a left endpoint approximation, the point to the far right will not have a rectangle of its own. So essentially what we're going to do now is just what we did before. We have 8 total rectangles if you include those 2 that have a height of 0. There are 8 total. You can count them up to be sure if you don't trust me. And we're going to go one rectangle at a time and do the width times the height for each one of them. Now the width is always going to be consistently 0.083, okay, because every 5-minute interval is 0.083 hours. And the height is simply we're going to get from the velocity values they give us here. All right, so as I write it up, you might want to be checking out the table you have a copy of. All right, so the total distance traveled, remember that's really what we were finding here. Since this was a velocity problem, when we're finding the area under the curve, really what we're finding is the total distance traveled. And notice we need to include that approximately equal to because it's only an approximation. All right, so the first rectangle had a width of 0.085 or 0.083, excuse me. And that first one, remember, had a height of 0. So that's your first rectangle. Second rectangle, width of 0.083. Now the height of that one, okay, it's this one right here. The height we're getting from this one right there. So we need to refer back to the velocity Mrs. DeConti was going at 5 minutes. So that would be 25. All right, third rectangle with a 0.083. We need to refer now to this height, okay, because this is your third rectangle. So we need to refer to the velocity Mrs. DeConti was going at 10 minutes, which was 60 miles an hour. Hopefully she was on the highway at that point. And we just keep going for each of the other rectangles. So now we're up to the fourth rectangle. That had a width of 0.083. The height was still 60, still on the highway. Next rectangle, 0.083 for the height. Now the height of this one, all right, this is another one, remember, where the height was 0, right here. We're talking this one right there. So that was your other rectangle that had the height of 0. Next one, now we're referring to this height right here. So that's corresponding to the velocity at 25 minutes. So that's 50 miles an hour. Two more to go. The next rectangle, she was back to doing 60 miles an hour. And finally, the last rectangle, she was going 35 miles an hour. So if you go ahead and number crunch those, you can double check. And remember, we were trying to find the total distance Mrs. DeConti traveled, so this would be approximately 24.167 miles. So now we're going to do the same problem, except now we're going to utilize a right endpoint approximation. So you'll notice the picture's still the same. That hasn't changed at all. But now the way in which we draw our rectangles are going to change, because now, since we're doing a right-hand approximation, a right endpoint approximation, when we do our rectangles, now we want the upper right corner of each of them to hit the points. So now the first rectangle going from 0 to 5 minutes, we need to align it with this point right here. So it's the upper right corner. So 5 to 10 minutes, now we're hitting this one up here. 10 to 15. Now the rectangle that goes 15 to 20, now you're back to having one that has a height of 0 again. 20 to 25, it's going to align with this point up here. 25 to 30. 30 to 35. And then finally 35 to 40. Now remember when we did a left endpoint approximation, we said it was the far right point that did not have a rectangle assigned to it. Now that we're doing a right endpoint approximation, it's the point on the far left that does not have a rectangle assigned to it. But otherwise we're doing the same thing. We're still going to, each rectangle in this case still has a width of 0.083. The only thing that's changing is we're using different values for the heights. That's it. So we're going to go through one rectangle at a time again. One way you could, if you wanted to, it's entirely up to you. You might have noticed back when we did this earlier problem, essentially what you have is the 0.083. You could factor that out as a common factor and then just really add up the sum of all of the heights, that would be perfectly good to do that. Some people like to do that, some don't. Some prefer to go just one rectangle at a time, so it's entirely up to you. Some people find it easier doing this way because then it's a process they can use if you do have a true Riemann sum where all the widths are varying and you really have to go one rectangle at a time anyway. So maybe we'll just continue with that. All right, so let's get started. We're finding once again and approximating the total distance traveled. All right, so first one with 0.083. The height of that first one is going to correspond right here to the velocity Mrs. DeConti was going at 5 minutes. We have to go back to our table. So that's 25 miles an hour. All right, second rectangle, same width. Now she's going 60 miles an hour. Third rectangle still going 60 miles an hour. Those are the two rectangles side by side that were the same height. Next one, now this is where we hit the rectangle that had a height of 0. Next rectangle, she was going 50 miles an hour. Now she's back to doing 60. 2 more. Next rectangle, 35 miles an hour. And finally, the last one, she's going 15 miles an hour. So if you add these up, you should get 25.315 miles. Now notice how that compared to the earlier answer. That earlier answer we got was 24.167. So considering that one is probably an underestimation and the other is an overestimation, probably the true distance that Mrs. DeConti traveled lies somewhere in between these two values. You could definitely average the two together to get maybe a better approximation. That would be certainly permissible to do that. All right, so hopefully by now you're coming to the realization that if the norm, that width of the widest rectangle, is approaching 0, and therefore we have n approaching 0, or infinity, meaning we can fit more and more rectangles under the curve, you can obtain a more accurate approximation of the area under the curve. Geez, it's a limiting effect. As the widest rectangle gets skinnier and skinnier and skinnier, basically n is approaching infinity, you're getting a better approximation for the area under the curve. It really is a limit. So what we could say in mathematical notation is that the area of a region, A for area, is going to be the limit as the norm approaches 0, or you could say as n approaches infinity. You could have either one down there. All right, so the true area of a region is going to be given by the limit of the summation of the areas of the rectangles. That's what all this summation is, remember. That's exactly what we were just doing and going one rectangle at a time and finding the width times the height for each one and adding them all up. So this is simply saying it's the limit as the widest rectangle width approaches 0, or as n approaches infinity, of the summation of all the individual rectangular areas. Now the function f is going to be defined on a closed interval. If you look back to all those examples we just worked, you were always told what the left and the right endpoints to use were. So that's going to be the closed interval from a to b. Then we have a new definition. We have the definite integral of f defined to be that limit we just talked about. So, I mean, take a look at the limit notation. As nice as it is and pretty as it is kind of cumbersome. So what we have is a new mathematical, I guess, function, you could call it, defined to be the definite integral. Geez, and it looks like that same antiderivative symbol we had before. Except notice you got now little numbers here at the bottom and the top of them. We didn't have those before. Now you do. All right, you might remember us talking about an antiderivative. Another expression for that is an indefinite integral. You might remember me mentioning that. Now that we actually have an interval over which we are finding the area under the curve, we simply have these little numbers at the bottom and the top of that antiderivative symbol. So A and B are referred to the limits of integration. A is the lower limit of integration and B is the upper limit. And that antiderivative symbol we talked about, you might remember me saying it looks like an elongated S for a reason. Well, now you know the reason. It's an elongated S because it's representing the sum of the areas of all the individual rectangles. That's really where that symbol came from. So yes, that same symbol was used to denote an antiderivative, and that's because the way in which we are going to soon evaluate a definite integral is by doing an antiderivative, and that's what your next thing you're going to learn is going to be. And you're going to see this stated in something called the first fundamental theorem of calculus. Of course, we like to abbreviate everything in math, so you're often going to see that as FTC1 because we don't like to write too much. So right now, the big thing you need to realize is that what a definite integral is going to be a number. Okay, it's representing an area under a curve. Think back to everything you did with antiderivatives. When you found antiderivatives, remember you always had an equation for an answer. That's a big thing you need to realize right now, is when you have a definite integral, the interpretation is that of area under a curve. So you're going to get a number answer. If you're doing a true antiderivative, an indefinite integral, you're talking about that other interpretation we talked about then of working backwards and finding the equation of the original function from the derivative. It's a family of functions. So where we're going to go next then is to talk a little bit more about this connection between how to evaluate a definite integral and why it is we can evaluate a definite integral by using antiderivatives.